So basically, the idea that I really want to put forward in this talk is it's not so much the sort of like that we're not good at implementing sort of like topography implementations and stuff like that for our land seismic imaging frameworks. In fact, we've been doing this quite effectively for about 20, 30 years, probably even longer. Right, but the problem actually is not so much that our implementation is good, right? It's the fact that we are building our implementations as these very sort of like low-level, fiddly technical things that you have to implement from scratch every time. So, right, so we have all of these papers showing all of these different surface treatments, but actually, in practice, people don't use them so much, right? Because they're tedious to use. And they really just make the complexity of your sort of like whatever imaging framework you put them into just completely blow up, right? And as we all know, an imaging framework is already a fairly complex thing. So basically, we're going to work from right to left because this made sense when I wrote these slides. But basically, what we have is, when we have these land seismic imaging frameworks, is we have a lot of algorithmic complexity, right? You have your FWI or whatever. It's got, all of your snapshotting in it. It's got your imaging conditions. It's got your inversion strategy. It's got all these fancy propagators, and suddenly we're trying to throw a whole lot more complexity into this by adding these topography implementations to the propagators. And yeah, okay, we can do this with like 500,000 lines of Fortran, but generally speaking, this is not how we want to go about it, right? If we want to make very complicated things, especially software, well then we need to introduce some sort of layers of like abstraction, some layers of automation, so we're dealing with less than 500,000 lines of Fortran. But to actually do this, well, we kind of need to know how to so in this case, right, this is like saying, well, we need an abstraction for topography, right? We need an abstraction for building these topography treatments. But then the problem there is you kind of need to know how you actually go about putting it together. So, for example, this idea of like a meta method. So in the case of say a finite difference, this is the idea of, well, if I hand you, a partial differential equation or whatever, you can go by hand. You can discretize that with finite differences, right? And you know effectively the algorithm by which one goes from like a continuous PDE to a discretized one, right? And this is the same sort of idea here, right? If I want to say take some set of boundary conditions or some geometry, how do I go from that to a particular implementation, right? And to do that, we need this sort of like generalized mathematical method rather than having a very specific method. So we want like an immersed boundary for this free surface, for this equation, for this discretization, right? We need something that's much more generic and abstracted. So, but why do we care about this at all? Why do we care about topography? So if we have topography, like topographic effects, so this introduces a bunch of extra things, essentially in terms of your waves are going to propagate very differently, right? They're going to have these very complicated multiple reflections. You're going to have shadow zones, things like this. And we can deal with this in two ways, right? We can pre-process to kind of try and get rid of these effects, which from an information perspective, you're kind of destroying information, you're throwing it away. Or we can say, well, in our FWI or whatever, we actually want to include the correct kinematics. And we see that actually this is probably a good idea. So if we look up here, well, if we incorporate topography in this inversion, we get very good resolution. But once we neglect it, particularly as the topography becomes sort of more rugose, we see that basically this, especially the shallow subsurface thing, just goes completely to hell. And even for very gentle topography, right? If you look at the scale bar on this, it's 15K across 3K deep, and it's very rolling, but we still see that actually having the correct surface geometry and kinematics results in substantially better imaging. Right, so we really want this topography, right? But we kind of recognize that it's a bit of a pain, right? Because we, as geophysicists, we really, really, really love structured finite difference, right? It's great, it's fast, it's fun, it's easy to implement, but the problem is we can't really reconcile irregular topography with regular grids very easy. So this is just a very simple sort of demonstration of this here. This is not the best contrast on the screen, but this is like a smooth surface, right? And we see that if we try and have this represent the smooth surface as just sort of like a naive staircase implementation with our regular grids, Well, it's actually really noisy. We have all of these like scattering, all this sort of like spurious scattering noise up here, right? But this is smooth. So intuitively we know that this should be smooth. And basically the reason is because when we take this smooth surface and discretize it onto a regular grid, this is all now steps. And this error does not get better. So what can we do? So we can come up with some wacky curvilinear grid like this. But actually this sort of thing, this is like a really nice one. This is fairly conformal. But so usually what people do is something called a flattening transform. And a flattening transform isn't very nice. It's hard to do, right? Because you end up with ugly transformed equations. But it's also not very accurate because you get problems with like grid skewness. You get issues with like resolution. You can see here you've got squashed in resolution here and it's all stretched out here. And so this is actually really hard to devise for any, like for substantial real topography. And yeah, obviously we can do SEM, FEM, and this is fine, but we do also have to think about meshing then, right? And it's also more expensive than our cheap and cheerful finite difference. So what else can we do? Well, we can steal some ideas from computational fluid dynamics, because it turns out they're sort of better at this than us. So they came up with this idea of an immersed boundary, where basically what they did is they said, well, we've got really horrible things to mesh, like porpoises and hearts, and like dragonfly wings and fish and things like this. So what we're going to do is we're not going to bother meshing it. We're going to just have a regular grid, right? And we are going to basically modify all of the finite difference operators along the surface, so that they basically respect the position of the surface and the boundary condition that should hold on it. And we can essentially apply this in Seismic as well, so like so. But then this means that, hey, we have no meshing, right? We have no meshing. We also have no curvilinear transforms. This is quite nice and easy comparatively. And it also fits into the sort of modeling workflows that we are used to, right, and that we like to use. So this was meant to be an animation, but PowerPoint mangled it, so we'll skip over it. Well, but basically, yeah, I'll just explain how the immersed boundary actually works, which is what this was meant to show. So essentially, if we've got like a wave coming in this way, the idea of immersed boundary is it's kind of like an image method. You're basically trying to create, like, say we've got a wave coming this way. Well, we're trying to create like another fictitious field coming this way that interferes so that the boundary condition is held on the surface, wherever that surface might be. So this is a kind of very simple example. We're literally just going to think about this for like a 1D wave equation, second order discretization, because anything else just gets way too complicated for a PowerPoint presentation. But yeah, so we've got our wave equation. We have our nice little 3-point second derivative stencil, right? And well, as we approach the end of the domain, this stencil is going to get truncated, right? And if we just have some arbitrary domain, that's not necessarily, right? The end of the domain is not going to necessarily line up with the grid. So we have this point here, which is just outside the grid. We have no value on that. So effectively what we need to do, right, is we need to devise some sort of fictitious value to go here to complete the stencil such that these two boundary conditions here still hold. And how do we do this? Well, we can basically take like a Taylor series, say like a second order Taylor series, and well, we have these two interior constraints still. So we can form up these top two rows using the Taylor series and approximating these two interior constraints. And we also have our boundary here with these two boundary constraints. So we can also approximate these with the Taylor series, and we get these two rows, right? And we form this little matrix system. And so what we can then do is we just invert it. And this gives us the derivatives that we need. But ideally, we don't really want to be switching up the derivatives. We kind of want to just sort of get a value for this. So what we can actually do is we can, effectively by doing this, we've fitted a second order Taylor series polynomial, in this case, to our interior data and our grid points. And effectively we can just extrapolate that out onto this final point of the stencil. So we can get a like an expression for the approximate function value at this point, and then substitute it back into our stencil expression, right? So this is fairly nice and straightforward. But the problem is, like in practice, this is a lot more complicated, as many of you will probably have guessed. So yeah, when I started my PhD, we kind of thought, well, you know, we can implement this for like acoustic, we get an acoustic-free surface, and then we can like slap it on other things. But it turns out that's not how it works. So we have like lots of different PDEs to solve because we keep coming up with new ones, like new kinds of TTI and all sorts of stuff. We have lots of different boundary conditions because an elastic-free surface looks completely different to an acoustic-free surface when you actually work it out on paper. And we have lots of different discretizations, right? We have lots of different like stencils that we want to use. We have lots of different ways of doing time stepping and so on and so forth. We have so many combinations that we can do. So you just get this sort of like explosion of combinations, right? Which is part of the problem that we had before, is someone would come up with like a nice particular implementation, and it would be really difficult to generalize out to anything else. And you also have this massive implementation effort associated with making a new topography implementation for all of these things, which is not, it's not what we want, right? So basically, we've got this enormous implementation complexity, and our productivity is essentially falling as we increase our numerical sophistication, right? We're sinking more and more and more time into developing these things and getting less and less and less back for that time. And basically, topography implementation is essentially just going to become disproportionately time-consuming as we start to do this. And we all know that that's not really what pays our wages, right? Like, if you're a geophysicist, you want to be coming up with like nice imaging conditions or cool new FWIs. You don't want to be sitting around fiddling with like making your propagator a bit more accurate. So, wrong button. So what's the trick? So basically, if anyone remembers John Etgen's 2022 keynote here, so he's basically talking about like, well, what would an industrial revolution in scientific computing look like, right? What would give us exponential progress in scientific computing? And the big thing that he kept coming back to is this idea of, well, you have machines that make machines that make machines in an industrial revolution, right? You don't just, you know, we didn't go to making more manufactured goods by simply, you know, having one person at home working harder. Well, we make a machine that makes that, and you make a machine that makes that machine, and so on and so forth. And we can apply this same property to this sort of same philosophy to anything, including software. So the idea here is we say, well, these topography implementations are fiddly, they're hard to come up with, they're hard to implement, but we kind of know how they work, right? We just don't have the time to actually build the things. So we automate it, right? We say, well, we make this like automated boundary treatment that takes some description of the kind of surface that we want to implement, and it spits out the operators that we actually want at the end, right? We don't have to care what's inside that, at least from a user perspective. And so, well, what does this allow us to do? Well, it means that if we want to build an imaging framework on top of this is suddenly radically easier, right? Because we're not mucking about with some fancy propagator, we're just getting stuck straight into actually building our imaging framework. We also, because we now have this like nice framework that's in common between a bunch of, you know, every time we build a new piece of software, like imaging framework, we're still reusing the same block, the same library, the same bit of code. So we have a massive reduction in this bespoke code, massively increased code reuse, which is always nice because there's less code to maintain, less stuff to go wrong. And it also means that if you're a specialist scientist, right, you don't have to deal with things that aren't really in your wheelhouse, in your area of expertise. You can just sort of pick it up and run with it, which is really good for sort of like productivity and actually creating innovation, right? So what does this look like? So from a code perspective, this is basically what you deal with as a user. So we have, say, these boundary conditions from before. So we have just that like u is 0 and sector derivative of u is 0. And we have this nice sort of like high-level Python interface, right? So we say, well, we have a boundary geometry, which we build from a signed distance function, which has some nice properties. They're easy to build. They don't lose precision when you discretize them. Nice things like that. And then also, you basically just pass these boundary conditions as a set of equation statements, right? And you can build this boundary, and then you just say, well, give me the modified operators for this particular finite difference operator. And it goes away and does that and passes it to you as an algebraic substitution, which you can shove into a De Vito operator. So just as a demonstration of the sort of thing that we can do with this. So basically what we're going to do is take this and build a nice gradient. So we've got our, well, this is Marmusi with about a K of topography shoved through it. Looks kind of pretty, like somewhere in Arizona or something. And this is our smooth model, right? Like our starting model that we're going to use to build this gradient. So this is just like a single gradient for one iteration of FWI, just to demonstrate the point. This is the sort of shot gather that you get from that, and you can kind of see that it's a mess. As I was talking about before, so you have all these like features like this, like shadow zone here. Your first break isn't a straight line, and all of this fun stuff, which messes up your inversion if you don't account for it. So Well, we see that actually when we get this gradient, it's pretty good, right? We've got a lot of we can use this framework, and yeah, we can build this like nice FWI gradient. We can see that actually because we've got this nice topography implementation, we've got a lot of sort of like very good resolution, particularly like if you look at this little section here, and you've got a lot of this like sort of fine texture. You can also follow. If you look at the original model, you have like this block here, and it goes through the fault blocks. And we can see that we still have that in the, and we can see that we're resolving that properly in our gradient as well, despite having, yeah, like a K of really complicated topography on top of this. And yeah, this is just Laplacian filtered to sort of like bring out the like the edges in it essentially, so you can see the details. So you can see that this is actually really good, and this was thrown together really quickly. I think this took me like a day, 2 days, something like that. Really, really not very long to put together from nothing. But yeah, as I mentioned before, like so we can see what we can do with this, right? But I think we'll probably want to know a bit more about how it works, because like that matrix system I showed you before is quite simple, and yeah, we don't just have like a second order 1D free surface to implement most of the time. So basically, well, the first thing that we can do is we can say, well, we like really, really high order finite differences, high order discretizations. So we want higher order Taylor series. So we can do that. That's quite easy. Essentially, what happens is, think of that matrix system that we had before. Essentially, all we're doing is making it wider, right? So if we make it wider, well, it still needs to be full rank, still needs to have a unique inverse. So we need more interior values. So we just have some arbitrary set of interior values, some bigger set, and effectively all this is doing is making this chunk, this like block essentially, which is the interior constraints. It just makes that taller. And again, we can have more boundary conditions, right? So we can have, you know, if we go to higher order, we might want higher order boundary conditions to stabilize our extrapolation. And again, all of this does is basically it just adds more of these like these boundary condition blocks essentially. And again, we can go even further with this. So we can say like, oh, we want higher dimensionality, right? Where we want to be in like 2D or 3D or however many dimensions that we care for. And again, all this is going to do is we say, well, we take like a 2D Taylor series expansion or a 3D Taylor series expansion, et cetera, et cetera. And again, this just gets wider in the same way that it would if we pushed up the order. And again, because we're now in more dimensions, right, we don't just have one boundary point, we end up with like a whole bunch of them to sort of express the geometry of the surface. And you'll notice that I said boundary points and not like a boundary surface. And so this is kind of the way that we think of it, is rather than having this sort of like continuous boundary surface, well, you just say we have a bunch of discrete points that are on this surface, right? They're not on the grid, but they're on the surface. And we are going to impose the boundary conditions at all of these points. And we just have some sort of like algorithm to say, well, we're just going to cull the ones where they're getting too closely packed to avoid, you know, any unpleasant forcing. And then, yeah, and we pick our interior points where we just say, well, we extend some sort of like hypersphere, so a circle or a sphere, or I guess a line in 1D. And we pick all of the interior points that fall within the circle, and we're going to use those as our interior constraints. So then we can pretty happily like build this system for all sorts of things, like all sorts of dimensionalities, all sorts of sets of boundary conditions. We can also do things like this. So we can do like coupling. So we can say that we have zero divergence on the surface, which is going to basically, it creates like a relationship right between different fields that has to hold on the surface. And we can do that too. So basically we say that, well, with this V, so we're going to have like Vx and Vy in 2D. So we're going to have a separate Taylor series extrapolation for both of those. So a separate Taylor series that we're fitting for both. And if we just had those two Taylor series right, you'd just have this sort of like block diagonal structure to the matrix. But then if you introduce this, effectively what it does is it's going to connect those two blocks together. So then you just have to invert this whole system as one rather than doing them separately, right? And again, you can do all of this sort of stuff. You can basically build a piece of code that just assembles these matrices according to the boundary conditions that you fed it, and then inverts them, solves the system, figures out what the exterior values are meant to be, or at least specifically, it creates the operators which figure that out and then, yeah, feeds them to the finite difference kernel. So then, yeah, what can we do with this? Well, we can do all sorts of stuff. Now we have this sort of this sort of like framework because, yeah, we have like this generic boundary framework, so we can do all sorts of stuff. We can do like second order acoustic, we can do a free surface, we can do a rigid surface as well if we felt so inclined. We can do, yeah, so this is like, for example, second order elastic TTI, and this is, again, this is using the same code base, right? It's just specifying a different set of boundary conditions that have to hold on the surface. And so yeah, we can really like push the complexity without really needing to rewrite anything. It's also helpful having this high-level interface because actually when you start dealing with like elastic boundary conditions, the proper free surface conditions, especially the high-order ones, get really, really ugly. So actually having this nice framework is very, very important for managing this complexity that you're introducing. And the other thing is, it means that you can like very easily prototype, right? You can very easily swap things in and out because, so the first things first is you've got this like, I mean, you're retaining your regular grid, right? So firstly, you can now flip your boundary implementation on and off like on a switch, essentially, because it's just something that you're adding into this sort of like your standard propagator rather than having to completely rebuild your propagator to reflect the fact you have a complex geometry. So in some ways that makes your life easier, it makes prototyping a lot more straightforward, but it also means that you can do things, because you can now just generate boundary implementations for whatever kind of topography you have, for whatever sort of implementation you want to implement, whatever sort of PDE you want to solve. It means that you can basically swap them in and out really quickly. So we can kind of see here, well, we've got Fletcher-Dufowler, and if we don't like Fletcher-Dufowler, well, we can swap it out for simplified pure QP. And it's basically trivial, right? Because we're not having to rederive all of this stuff and re-implement it all. It's just handled automatically. And this basically gives you a lot more flexibility in terms of like prototyping, innovating, that sort of thing. So yeah, I guess in summary, it's this idea of, well, if we want to implement topography, right, and we want to do this in practice, we really need to think about having these sort of like high-level abstractions to do so, rather than sort of trying to go at it at a really sort of like low level with particular implementations. But to do this, we basically need to have like automatic, we need some degree of automation, right? Ideally, we want to be deriving these sort of like these boundary treatments automatically rather than having to hand drive them every time and hand implement them every time. And so, yeah, generally speaking, I would say that like this sort of like idea of a generalized immersed boundary implementation is the way to go. So rather than curvilinear grids or anything like that, I think this like immersed boundary treatment is a much better fit for the way that we do things currently, and sort of fits much nicer onto the codes that we already have and the paradigms that we already have. So in terms of what we plan to do in the future with this, it's mainly performance. So we've basically demonstrated that, hey, we can, we can build this thing and we can apply it to all sorts of problems. So the next thing is to figure out, well, we've made it general, how do we make it fast? And I think this should be reasonably straightforward. There's a couple of different things. So in terms of mathematical reformulation, so you might have noticed that when I was showing the system before, it has a pseudo-inverse in it. In practice, you never want to invert a matrix if you don't have to. So I need to look at that. And just generally in terms of the pre-processing strategy, there's a lot of inefficiencies there at the moment, which can be cleared up. The other thing that's interesting is because what you basically have is this thin skin of modified operators. So ideas of saying, well, what's the best way to iterate over that, right? Because you just want your normal operators in the interior, and then a very efficient iteration over your thin skin of boundary operators, right? So I think like research in terms of figuring out, well, what's the best way to do that? What's the most efficient optimization, sort of like iteration pattern for like memory, locality, and all this sort of fun stuff. And also, yeah, ideal numerical schemes, and yeah, like further use cases, I suppose. So I think with that, we are probably on to questions, finally.
Questions?
Equation you have, right? You have when you have this condition, and
and you have three terms. You have u, very beginning.
Which one is that?
So you have three, I think, u, yeah, x, yeah, go back.
This one?
Yeah, so if you go on this one, so you have ux minus 1, ux 0, and two others, they are 0.
Pardon?
And
this one here?
Yes, but, okay, so if you go down, why these two are zeros?
So if you think of...
Because you don't know them, or we are...
no, so if we take a Taylor series, so we are expanding this Taylor series around x naught. So if we expand u at x naught around x naught, we just get u at x naught equals u at x naught plus 0, 0. So when we form up this matrix system, you just have 1, 0, 0, because that interior constraint is at the same point that you are expanding the Taylor series.
So it doesn't mean that it's 0 because you don't know it.
No, it's literally just if you expand if you do the Taylor series expansion at that point,
okay,
and then you end up with coefficients 1, 0, 0, 0.
All right, I got this part. Thanks.
Okay.
The other thing I have, so when you build an operator, right? I mean, like second derivative, or do you guys? I mean, do you provide any? I mean, a condition for delta x, delta t for the stability, or this is a user has to deal with that based on whatever?
As far as this framework is concerned, it blindly builds whatever you ask for, right? So it's sort of down to the users to check that is sensible. It will. One of the things that we did realize is what's the best place to point this out? So one of the things that we did notice is we did find that it's useful to add a threshold, which essentially says that if an interior point is too close to the boundary, you just ignore it.
No, I mean, if I have to implement it, for example, you provide a scheme, all right, to compute derivatives. I have to implement it. I mean, I have to write a code based on this, or you generate a code. So when I'm going to give a value delta x and delta t, or delta y, delta z, I mean, who is going to guarantee that my scheme is not going to explode, or I'm not going to...
That's down to you as a user.
Okay, all right, okay, whatever. Okay, thanks.
All right, any other questions? All right, thank you very much.